A research facility in Pasadena, California, January 1986. The engineer reviewing the telemetry from Voyager 2 is looking at data that has just arrived from a distance of nearly 2 billion miles, and that has taken almost 3 hours to reach the Earth at the speed of light. The spacecraft is approaching Uranus, a planet that no previous spacecraft has visited, and the cameras on board are returning images of a world that the astronomical community has barely been able to observe from Earth. The mission profile calls for a brief encounter lasting only a few hours, after which Voyager will continue outward toward Neptune and eventually toward the boundary of the solar system. The engineer is reading the data with the awareness that the spacecraft cannot be reached for service, cannot be returned for repair, and that whatever it captures during the next few hours represents the only opportunity for direct observation of the Uranian system that humanity will have in his lifetime. This is the story of how two small spacecraft launched in the late 1970s with technology that was already approaching obsolescence at the moment of their construction became the most successful planetary exploration mission in history, returning data from the outer planets that has not been matched by any subsequent mission. The Voyager program had been developed at the Jet Propulsion Laboratory through the early 1970s, taking advantage of a rare alignment of the outer planets that made it possible to design a single mission that could visit all four of the gas giants. The alignment, which occurs approximately every 176 years, would allow a spacecraft launched in the late 1970s to use gravitational assists from Jupiter, Saturn, Uranus, and Neptune to reach each subsequent planet without requiring additional propellant. The opportunity was recognized in the 1960s, but the funding for a full Grand Tour mission was not approved by Congress, which authorized instead a more modest program that would visit Jupiter and Saturn, and that would, if the spacecraft survived, be extended to the outer planets on a best effort basis. The two Voyager spacecraft were launched in August and September 1977 from Cape Canaveral, with Voyager 2 actually launched first and Voyager 1 following 16 days later on a faster trajectory. The spacecraft were nearly identical, each carrying a suite of cameras, spectrometers, magnetometers, and particle detectors designed to characterize the planets and their moons during brief flyby encounters. The total mass of each spacecraft was approximately 1,700 pounds, with about 115 pounds dedicated to scientific instruments. The power came from 3 radioisotope thermoelectric generators, fueled by plutonium-238, which would provide steadily declining electrical output for several decades. The encounters with Jupiter and Saturn in 1979 and 1980 and 1981 were the original mission and were considered the principal scientific objectives. Both spacecraft returned thousands of images and produced discoveries that reshaped the planetary science understanding of the outer solar system. The active volcanism on Io, the dynamic ring system at Saturn, the complex atmospheres of both planets, and the variety of moons orbiting each system were documented in detail that no previous observation had approached. The success of the Jupiter and Saturn encounters provided the political justification for extending the missions to Uranus and Neptune. The extension required the spacecraft to be reprogrammed in flight, with new software uploaded from the Earth that allowed them to compensate for the deteriorating performance of various components and to make optimal use of the limited communication bandwidth at the increasing distances from the Sun. The engineering teams at the Jet Propulsion Laboratory developed techniques that the original designers had not anticipated, including image compression algorithms that allowed more data to be returned within the available bitrate, and pointing techniques that compensated for the increasing exposure times required at the lower light levels of the outer solar system. The Uranus encounter in January 1986 returned the first detailed images of the planet, its ring system, and its moons. The Neptune encounter in August 1989 did the same for the outermost planet that the spacecraft would visit. Both encounters produced data that has not been duplicated by any subsequent mission, and as of 2026, no spacecraft has visited either planet since the Voyager flybys nearly 4 decades ago. The spacecraft themselves did not stop operating after the planetary encounters. Both Voyager probes continued outward, returning data about the conditions of the outer solar system, and eventually crossing the heliopause, the boundary between the influence of the Sun and the interstellar medium. Voyager 1 crossed the heliopause in August 2012, and Voyager 2 crossed it in November 2018, with both spacecraft continuing to return data from interstellar space. The Voyager program did not represent the most advanced technology of its era, and the spacecraft are now operating with electronics and software that would have been considered obsolete in 1990, but they gave humanity through more than 4 decades of continuous operation, the only direct observations of the outer planets that any civilization on Earth has ever made. And the data they returned remains the foundation of essentially everything that is known about the outer solar system from direct measurement.